Hello viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're gonna talk about Parker Solar Probe. So let's dive right into it. Now, recently this puppy came into news simply because there has been a big event. So what is this event? Well, reality is it touched the upper solar atmosphere. Now be mindful, it has touched the atmosphere, not the photosphere which you actually see. Be very mindful of that. Now, how do we define where that quote unquote atmosphere is, or like begins or ends? Well, there is a simple mathematics. Basically, if you have solar wind leaving the sun, that simply means it's outside of the influence of the magnetic field and basically gravitational well. So if you are basically if you are outside of the atmosphere, you will find all the solar wind going outside. When you are in the atmosphere, you will find them them interacting and going backwards or forwards, because again at that point sun is in charge. If solar wind is under the jurisdiction of sun, you have touched or basically quote unquote entered the sun atmosphere. That's what happened. Now what do we call that boundary layer? We call it alpine critical surface. Now this happened on 28 April 2021, and this was around 18.8 solar radii. Now that number is very odd, and unless you know exactly how sun big is and then how many times 18 you do that, you will not understand this. And kilometers, millions of kilometers, yeah, that also does not translate well. However, I figured out one interesting way. It was 43.5 light second away. Now how far is that? Well, think of it this way. Basically sun from earth is 8.3 minutes away, meaning 498 seconds. So that should give you an easy contrast to understand basically how close this puppy went compared to us. 498 seconds, 43.5 seconds. So this puppy went close. I mean, really freaking close. So if it tries to communicate to us, it will take 8 minutes. So this puppy went really close and entered the solar atmosphere. That's why we classify this thing as the first thing that actually quote unquote touched the sun. So how it was built though, so it could survive the touching of the sun? You have to understand one aspect of it. Recently we have been talking a lot about James Webb Telescope and its Sunshield. Now James Webb Telescope is very far, meaning 8 light minutes, more than 8 light minutes, almost 8.5 light minutes away. Now benefit, it's far, which simply means all it has to deal with is photons. Now thankfully our star, meaning our sun, is not very bright in high energy photons, meaning if you look at through X-ray, it has X-ray, but it's not like GG amounts of X-ray, it's not GG amounts of gamma rays. Those generally happen in much powerful, much brighter star. However, when you start to go down in photon energy, you will find it's ludicrously bright in basically infrared. So majority of the energy is in infrared photon. So if you can reflect infrared, you're cool, you got this. So because of the distance and because of the inverse square law, all James Webb Space Telescope had to deal with is just photons, and generally majority of infrared photons. So it could just reflect them away, have multiple layers of them, so it can reflect, cool off, and it would reach to almost absolute zero. Awesome. But here's the deal. When you're talking about going to the sun, basically actually making a kiss to the sun, well, at that point not only you have to deal with photons on top of that, which will be much higher energy, because yes, at that point even X-ray photons and gamma rays photons start to add into the picture. You are talking about particles now, meaning you are talking about actual hydrogen cores, meaning protons basically hitting your stuff. You are talking about helium nuclei, meaning alpha particles touching your stuff. That is very serious. At this point in time, you're talking about actual wind hitting you. Solar wind is serious. At this sort of close distance, solar wind can actually just push you. So from Parker probe's point of view, it's actually getting heated by basically hot jet gun. Basically it's very hot. So not only you have to design something that can handle the photon, you also have to design something that handles the particle. That's the expensive part of this. Now, so shield was huge, basically 2.3 meters wide, and it's almost 11.4 centimeter. Basically the 5-inch ruler you buy, a little bit smaller than that, basically this thick. Now how did they make this magical shield that can survive the love of extra photons and boatload of love of particles? Well, they used carbon plate. Now it is a sandwich material, meaning it has carbon plate on both sides, one side and negative side. However, to make sure it survives the sun, it has white alumina coating on the sun side. So the white alumina is quite strong, quite durable, and it has the good reflectivity in, it's not very reflective, meaning compared to gold is very good in basically infrared, but really bad in other spectrum. And other things also have the same issues, like they are really good at one thing but not very good at general reflection. You want here something that can reflect almost everything. So white alumina was chosen, and it is very robust. However, it's only as robust as the thing you apply it on. So carbon plate was chosen because it has been used with space shuttle, which has survived re-entry. So it was something that is designed to handle high photon and high particle flux. So that's just the one layer. Then it has carbon foam. Now that carbon foam is thick, and it has to be thick so it can withstand the particle, because over time it will leach through it. Over time, the heat that is building up on the front side will slowly creep towards it. So you have to have thickness there. You can't just have empty space. You have to have actual thickness there. Basically, you are making a blanket, very capable blanket. So the sun facing side will reach during close encounters as high as 1300 degrees Celsius. That's hot. Like majority of the metals will melt at this kind of temperature. Now it will try to do its best, and is supposed to drop the temperature from 1300 degrees Celsius to 300 degrees Celsius. That's almost like your soldering iron temperature. Now you might be like, wait a minute, that's still hot. Well, it is. So to handle that kind of high heat flux after the Sunshield, the whole structure, the whole truss of this puppy was built on in titanium. Now why titanium was chosen? Well, simply put, you could not make it with aluminum, because while aluminum is light and strong, it does have consequence that it is really good conductor, meaning that 300 degrees Celsius that is on the other side of the basically foam will transmit very quickly to your whole probe. You do not want that. And steel could have been used, but again, you want something that is even better than that. Titanium has 1/4 the thermal capacity of iron, meaning if you have 100 watts of heat, it will take basically 4 times longer to transmit from point A to point B on titanium. So titanium was the best. Like copper simply could not have been used, aluminum will simply not be used. Steel could do that, but again, you want something lighter and better. Titanium was chosen. So the whole skeleton, quote unquote, has been built with titanium. Now at this point in time, you can manage the heat. You have a shield, but you're still at 300 degrees Celsius. That's too hot. So it has high temperature blankets. If you pay attention to any high resolution photo of basically this probe, you will notice that there's like a lot of foiling around it. Those foilings are specifically high temperature thermal blanket, meaning those blanket is the primary reason why 300 degrees Celsius drops down to 30 degrees Celsius. At this point, most instrument can handle that. That's why you will hear people, scientists talking about this, that it's like room temperature. That's what they are talking about. That from instruments point of view, it's like hot. It's not like, deep space cold. It's like, wow, like I got this. It's a, warm kind of scenario. And to make sure that this puppy has energy, they are using solar panel. Problem with that is that at that close to the sun, you apply solar panels, poof. Solar panel will go poof. So how do you make sure it does not go? First, you do not deploy it like this. So if this is the solar flux, you apply like this. You never go like, no, you apply like this. And you have titanium backing on that, which has microchannel, which has deionized water, meaning basically distilled water running through it. And that water is cooled through this giant space radiator. So without this radiator, that panel will simply not work. And the panel is also rather small. It's like around 300 watts. So it's not a huge panel. And they had to do this because otherwise, if they actually deploy the solar panel fully, poof, if they deploy a very large solar panel, again it will overheat. The radiator will not be able to keep up because it has to dump heat using photons, which it does work, but it's not very efficient. So you get that point. There is a serious limitation on this thing. That's how it was built. Now, after with all that engineering, you have to understand it cannot actually continuously orbit it. So if you have sun and you're like, I'm gonna orbit it continuously, yeah, your system is gonna melt in like 15-16 days, poof, it's gonna melt away. So it has to design in such a way that it has a very ludicrously elliptical orbit. Now that orbit allows it to orbit the sun in 88 days, meaning the whole one orbit is 88 days. But because of this very highly elliptical orbit, its quote-unquote sun flyby is only 11.6 days, and that's the first few flybys. As the it starts to increase its speed using Venus as a gravity assist, its speed will go up. So you will notice that speed in this axis, orange axis, it will start at like around 98 kilometer per second, and it will, the upper limit that we are expecting is 198 kilometers per second. That's ludicrously fast, and it will like have multiple flybys of Venus. Basically 7 Venus flyby have been expected. So far we have completed 3 flybys of the Venus, and by the time this video is coming out, the 4th flyby would be on the horizon. So as it will keep leaching off speed, it will also drop closer. Now be mindful, because it's getting closer, the exposure to the sun at that close distance will be harmful. So they are also shrinking the duration. So duration will shrink from 11.6 to 9.6. That's expected at this point in time. So that last flyby would be around that 9.6 system. Now Venus is also a primary, helper. Without it, we simply could not achieve that kind of ludicrous speed and that kind of close distance. And this is the first time I have ever seen anybody use gigameters. I know that you're supposed to use that, like instead of 1,000 kilometers or 5,000 kilometers, you're supposed to use giga. This is the first time I've seen anybody using that, like gigameters. So you get very close to that. And total 7 planet system should allow you to have multiple passes in each orbit, trying slowly getting closer and closer and closer. So you will get a lot of good data out of it. So that's why be very mindful. Yes, this is a good instrument, but it's not strong enough where you can just orbit the sun continuously. It cannot do that. So what about the guidance? How the heck you gonna guide something like this? You have to understand probe has a serious limitation here. It must maintain shadow, meaning the shield should be the only thing that's looking towards the sun. If anything else look towards the sun, most of them will turn into ash instantaneously. Blanket, poof. Titanium, it will last a bit longer, but poof. So you have to understand there is a very serious limitation on this thing, but it must maintain absolute orientation towards the sun. This puppy must be 90 degree, basically parallel perpendicular to the sun. It has to be there. That's absolute limit. So how they are achieving that? Well, they are using reaction wheels. So they have 3 reaction wheel, basically like this, and like this, XYZ, and 1 redundant backup system. And you have to understand reaction wheel has an issue that it will do amazing job, but after a while it reaches saturation, meaning the RPM has maxed out. You cannot push it further than that, and at that point your spacecraft will start to drift. To compensate for that, it has monopropylene hydrazine thrusters and a huge tank of it. Now that thrusters, you see all the red arrows, those are small thrusters of that. Now that thrusters will fire when you start to notice that basically RPM of the gyroscopes are reaching a point where they are dangerous. They're like, okay, gyroscope starts to low down RPM, and then it's going to use the thruster to balance itself out. So it does have a dead limit to it, meaning it will die the moment propellant runs out, because once it's done, gyroscope can only maintain it for let's say 0.25 AU. That's the point where all the science instruments starts to come online. It will start to do that, and by the time it's let's say 3 days into the mission, yeah, gyroscope would be completely saturated and won't have any fuel. It's gonna expose to the sun and poof. So it has a dead limit, meaning almost like James Webb Telescope. Basically, if it runs out of propellant, it's done. Same will happen here. So because of that serious limitation that the shield must face the sun, it has no proper reliable communication. That simply means it has to be 100% autonomous. And this flat out, every people who have worked into this, they say this with a pride that this is one of the most autonomous system out there in solar system. Flat out, everything we have sent, like we have okay, we're gonna control you, we're gonna guide you, or this, I got this. I got this. It's like, I got this. But the moment it crosses that 0.25 and science instrument deploy, it's like, I got this. You don't tell me what to do because you are freaking 8 light minutes away from me. I take care of everything. And that creates an issue. Because of that shield, during many time you will have a scenario where you have the shield, you have the sun, and then you have Earth. It's like, how the heck are you gonna communicate? You can't. So that's why you will see things that happen in April coming into December, because it has to wait for that 2.25 AU distance to be crossed. Then science instrument will shut down. Then it will start to downlink, and that downlink will happen over that remaining 70 days, and it will be very slow downlink. So that's the guidance part of it, and it has a dead limit. Be very mindful. Once the propellant run out, the end. If gyroscope reaction breaks, it can still use propellant to maintain the orbit, but it won't be very long lasting. That's why they have one backup system. And do not expect, if today is happening, if NASA is saying telemetry is showing that today we're supposed to be doing that sun bypass, does not mean NASA knows that. It could happen, something bad happens from 2.25 a, it will take them very long time to understand it. It's not coming on the other side. Yeah, something is wrong. So that's the guidance part of it. It's very complicated, and because of that Sunshield, it has to be absolutely inside its shadow. The moment anything else touches it, poof. So has it been a success? Well, absolutely. At this point in time, everything is working as predicted, meaning people said that we're gonna build this and we're gonna launch it to sun, and it can almost touch the sun. It did. It touched the sun's chromosphere, which, mind you, has higher temperature than the sun's surface, and it has survived. So that's awesome. And we have learned a lot. Even though the mission still has many years to go, we have learned a lot, and a lot of data is still in the banks that is being downloaded, and we still have to crunch through them. So amazing progress so far. And we already figured out there are kinks in the solar wind. This never made sense. You have a reactor, it's pumping out solar wind. Why the heck it has kinks? But it has it. Solar probe already proved that. And this is one of those things that you have to understand. Many times mathematics allows us to get very close to what is there, but sometimes you have to be there in order to be okay, what are its resolution data of it. Basically, think of this way: mathematics allows you to have 2 megapixel photo, and having actual probe, actual equipment going there gives you 50 megapixel photo. So that's the whole thing. That's why we make this sort of equipment. Like, we never in mathematics will figure this sort of thing out. Once we figure it out, now we add this data into our mathematics to make our mathematics even more high resolution. So this is amazing aspect of it. And one of the core question with sun is like, how the heck corona is hotter than the surface photosphere that, like, we see. It's like it's photosphere is closer to the core reactor. Why the heck that is not the hottest? Now you have to understand one core aspect of it, that same way how watts have two variables into that, voltage and ampere, same way it goes in temperature also, meaning temperature does not directly translate to a lot of heat. So if you could have like ludicrously high temperature, let's say 50,000 million billion degrees Celsius, does not mean it actually has that kind of heat. Like, think of this, like how which is hotter, your soldering iron, that is like 50 watts or 60 watts, or your room heater. But your room heater does not go to 300 or 400 degrees Celsius. Same thing happens here also. The photosphere, yes, it has a temperature, but it has more oomph to it. Now, a chronosphere, while it does have ludicrously high temperature, it does not have oomph. That simply means there was a sort of a step up voltage transformer. So what is it? This puppy figured out, like, because it actually went to it, is like Alfvén waves are the leading candidate at this point in time. NASA is like, yeah, at this point in time we are pretty sure that leading candidate wise Alfvén wave is the only thing that explains it, meaning apparently there's magnetic waves, and these waves are creating quote unquote tension into quote unquote plasma. And because the plasma is so spread out, that's why the probe is not melting. That spread outness allows the basically particles to vibrate at much higher, basically vibrations is the temperature, so it vibrates much more because it's free. It is free to vibrate. It's almost like how underwater sea vents, which could be hundreds of degrees Celsius, does not boil the water because water is held by the pressure. Same thing is happening to the apparently sun's core arteries. Like, the core surface is like, yeah, I don't have the luxury of vibrating at ludicrously high temperature. It does have boatload of heat, does not have the luxury of converting that voltage. So upper sphere does that. At this point in time, that's the hypothesis. Alfvén wave. More data, more flybys, more data crunching will figure this out. And some people have mathematically predicted there should be a dust-free zone around the sun, because sun has so much photonic pressure, I mean enough photons in like pushing it, that light dust particles should simply go poof. So this is confirmed that kind of hypothesis, and it's estimate is 18.7 light second away from sun. Basically, you take the sun, create a almost 19 second light second sphere. That sphere is 100% dust free. Only thing at that point in time would be visible would be solar, basically solar wind, nothing more than that. Again, unless something really huge like a planet start to fall into the sun, that, of course that will fall there. Sun cannot just poof a planet, but you get that point. So this was really huge success, and this is one of the other sun's solar observatory that has noticed that probe, because it's like a very good telescope looking very closely, and because of the shadowing effect, it's surprisingly easy to observe that Parker solar probe. So we know where Parker solar probe is, and the camera that is looking outside of the solar probe, basically forward of the solar probe, that's also doing amazing job at this point in time. So this is one of those missions that was done properly, with proper budgeting, under time, properly performed, and it's really giving us good data, and we are really looking forward to what it does in more closer flybys. So this was my presentation on solar Parker probe. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice or thrice if you want. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.